Okay, do you want me to get going then?
Yep, that looks good.
Great. All right, thanks. Yeah, so welcome everyone. Thanks for coming to this presentation. So yeah, Stephen introduced it as the principles of software design. I don't think I can claim any such sort of mastery or comprehension of everything. So I think this is just going to be some principles of software design, really. So yeah, let me just start by giving a little bit of background. So yeah, I'm Tom Hawes. I'm a research software engineer here at Exeter in the Research Software and Analytics group. And if I can just get the slides to move. Okay, so I think it's maybe helpful just to say a bit about where I'm coming from, because software design, I think, is such a can be such a sort of personal topic that people have sort of views on, and so it's always good to know where those views are coming from, I think. So I've been in an RSE for a couple of years, worked in a commercial consultancy for about 4 years before that, but really all of my software development work has been in a sort of research or research and development style setting. So in my academic background, so I have a doctorate in pure maths, so I tend to think very much in terms of abstraction and structures and like that way of thinking. And as far as software goes, really almost all my experience has been on software projects, things which have a particular start and a particular end date, and then there's some, and then software is essentially handed over, and the engagement with the customer or the person we're working with ends. I don't have really much experience working on software products, things which have a much more ongoing life cycle, and you're much more involved throughout the whole life cycle of the software, including when it's in sort of production use. So that's maybe something to bear in mind. And why I'm giving this talk, I suppose, is because software design and how we create software has been a real sort of interest of mine, probably harking to my kind of maths background, but it's just a subject I enjoy reading about, thinking about, and trying to reflect on how I do it in my own work. So I'm hoping that today I can just share really some of my own thoughts on, what I've been sort of thinking about as I've read things. So brief outline for this talk. So I'll start by talking a little bit about change and flexibility in software. I then want to move on to really just a few specific principles, and in some cases could view them as techniques for going about, well, designing software or that feature in the design of software. And I'm going to sort of, hopefully at the end, in the last sort of 5 minutes or so, kind of pull back and look at a sort of slightly bigger picture of the question of kind of evolutionary design versus upfront design, or at least just to raise that as a sort of distinction. So let's move on to the first part. So a little bit on sort of change and flexibility. So when I say, this is a sort of interest of mine, I guess this is most of, although not quite all, of the books I've at least dipped into. I certainly can't claim to have read all of these cover to cover. There's a lot of material out there on, perspectives of how we should design software and what's important to consider when we're designing software. And it's quite interesting that really in a lot of these, a huge sort of feature is made that a good design, in quotes for good, involves getting software in a state where it is easy to change and flexible. And this has come really, so I suppose down in the bottom right hand corner there, that old book Structured Design, so that's from the sort of late 70s. And that's one, probably not the first place, certainly, but that's one place where they make the contention, if you like, that the main cost of software is the cost that's required to change it. And this is a theme that has been picked up again and again by other authors, and people have thought about it, particularly in industry, although not exclusively. And so what are some of the kind of mechanisms by which software can change? Well, perhaps the first one we think about is, a change to requirements. So the person or the group we're working with, maybe suddenly say that, okay, we actually now quite like the software to be able to do this thing, maybe in contrast to what we'd said originally. So those kind of abrupt kind of, suddenly needing to take a turn in direction, certainly, is one avenue of change. But there are others as well. I mean, even as we're working, and this is something I've found, even as we're working on software and understanding the problem domain that we're trying to work in, our understanding develops over time, and the understanding we have about the particular intricacies or the problems that need to be solved are very different from the first week of engaging with someone to then, 3 months down the line, 6 months down the line. And so, we may well want to build that change in understanding and our, better understanding into the code we have, or need to revise our code in light of that. There can be other sort of extraneous factors as well. So maybe assumptions that we have end up kind of getting pulled from underneath us. So, maybe there's something like a big sort of data storage platform that we assumed would be provided by an institution is no longer available, and then we need to sort of pivot, and decide, okay, well, what are we going to do instead if we can't use that, and to what extent does that then impinge on the code, on the software we've written? Or it might be things like regulatory changes, particularly in sort of medical settings, or settings where we're dealing with, personally identifiable data. And then a final one, which I think, can sometimes be sort of taken, or overlooked rather, is that software we depend on can change. And this might be particularly relevant for some people, because I think it was just the middle of last month, a couple of weeks ago, that NumPy released their version 2.0 of NumPy, and there are a lot of breaking changes from version 1, which I'm sure a lot of code would have been written on. So things that we depend on changing is also a big influence on how our software can change. And the kind of one of the things that has come about really since the sort of 90s, 2000s, is a kind of emphasis on embracing this idea that, that things change in software projects. I mean, this is kind of, encapsulated here in the Software for Agile, or the Manifesto for Agile Software Development, where they talk about responding to change being more valued over following a plan. And while there is still value in following a plan, they put more emphasis and importance on being able to respond to change than necessarily to adhering to that plan. And then even a book, that was published around the year 2000, I think, Extreme Programming Explained, with the subtitle Embrace Change. So not just kind of change as a fact of life, but we should be actively embracing it. And so these ideas, I think, have kind of bled into then how we design software and make them, easy to check, and try to make our software easy to change, because that's what we maybe come to expect in a software project. So I'm going to talk about just, 3 principles really, out of a whole host that could have come, which have come from, my reading. But so I suppose I want to first say that I'm looking at software design very much from this perspective, on this question of, what techniques or approaches can help make software easy to change. In particular, there are certain things I'm not going to be talking about, like writing performance, code, and how does that either dovetail or even conflict with this idea of making software easy to change. So that's kind of a bit on the scope. But so I suppose if I just continue on to our first principle, Oh, okay, that was clearly an extra slide. I didn't mean to have in there. Never mind. So this first principle, so layers of languages. So, okay, of course we write software in terms of languages, in programming languages, but I'm using language here in sort of a different meaning. And it's more to do with actually creating languages to model and express software. So whenever we're trying to solve something, we're needing to conceptualize it. And one of the real sort of powerful techniques of being able to get some control over a problem is to start giving names to things and sort of build up a mental and explicit model, of what it is we're trying to do and how to express the problem. And so a key kind of concept is to try and use that sort of language to and to bring it over into our code and express it in terms of things like the, sort of classes we define, or methods or functions, even variable names, things like that. So we want to kind of express the language directly in our software. But more than that, it's not just about sort of a language. In reality, there's often different levels of abstraction of language, or primitiveness of language, I sometimes like to think of it. Some of the sort of high level concepts in our code need to be implemented in lower level concepts. And so you can have this sort of layering of different languages which are appropriate for different scopes of job, from the sort of higher level, which is maybe more expressive and more tailored directly to the actual sort of customers, if you like, problem that they're trying to solve, to lower level languages which are more general purpose but less specific. And I mean, if you go right down to the bottom, you end up implementing things in terms of a programming language, the fundamental parts of a programming language itself. So I'm going to be focusing on Python throughout this talk. So it might be constructs in the Python language. So I want to try and talk about a particular example for this, and I'm going to be looking at a script called Quarter, which takes in an image and then just splits it up into 4 quadrants. So this is the point where I need to switch over to code. Where can I get this? So I want to take a first look at some code here, and I'm not expecting to sort of go through and explain what each line does, but I just want to point out a couple of things. So the basic idea of this code is to load an image from a path given at the command line, to extract out the sort of pixel data for each of the quadrants in the image, and then simply to write each of those quadrants to a file with a file name based on the original file name that we got for the original image. I suppose the thing I want to point out here is that if we're thinking in terms of images that are getting sort of, cropped in particular, and then written to a particular path, the code here doesn't really express those concepts directly. In particular, this Python code uses a few imports and some third-party libraries. And in fact, it's not obvious from here, but where except maybe for the name, where I've loaded in fact, let's highlight up here. Where I've loaded in an image, it's actually loaded it in as a NumPy array. And in order to actually carve it up, I'm needing to work with that array and get data, and use the kind of API, if you like, that NumPy provides. But it's not necessarily really well tailored to what I want to do. So I can get the height and the width of the image from this attribute shape of the array. But I need to remember that the first element, so this is actually a tuple, I need to remember that the first element corresponds to the height, of that image, the second the width, and then the third is actually to do with red, green, blue values, which I'm not particularly interested in. I then need to know how to slice up the array. Now, I mean, there's a very intuitive syntax here, but nevertheless, in order to actually carve up that array, I need to know something about how the NumPy, library works. So I suppose the thing I want to say here is that we're using a language of arrays and some other things, which don't make it so easy to understand fundamentally what is the basic idea of what this script is doing. If I was to explain it just in words to you, oh, it loads an image, it cuts up into 4 quadrants and then just writes each of the quadrants out. Here the code is actually expressing it in terms of arrays, and I'm needing to kind of mentally map my idea of just what's happening to each image onto what that means in terms of arrays. Now, in a small example like this, of course, probably no big deal. But if you start talking about code bases, which are spanning thousands, tens of thousands of lines or something like that, having to continually do that remapping is going to be confusing, lead to problems, probably lead to bugs when you forget something, because it just can't hold all that in your mind. So here's an alternative implementation, and again, not wanting to go through all of the details here, I've introduced a class called image, and it has various methods. Well, it has one key method, crop, for cropping an image, and some attributes to more directly express, something I'm interested in, so the height of the image and the width of the image. So if I go down, the main part of this script now tries to express in a more sort of high level way what we're doing. So that, for example, we're first passing our command line inputs, we're then loading an image from a file, we're quartering up that image, cutting it up into 4 pieces, and then we're writing those 4 pieces to files. And if we look at the sort of main, the main function here, the workhorse function here is this quarter image function. And now we're starting to actually see the language that I might want to, use from the domain actually appearing more directly in the code here. So, for example, I'm getting, in order to work out the height and width of each of the quadrants, in order to ultimately crop it, I'm taking the height of the original image I had and the width of the original image and dividing them by 2. And then I'm being explicit in saying that I'm taking the image and cropping it at particular start points in terms of height and width coordinates, and cropping it according to the certain height that I want the cropped image to be and the certain width I want it to be. And so at the high level of the script, we're now using a language which is much more tailored to the problem we're trying to solve. But of course, if I go into the image class, okay, if I look at crop, for example, so this crop method, it's using an attribute of the class called pixels, which is in fact a NumPy array. And here, so I've still got the NumPy array slicing going on here that we had before. It's now featuring more as part of the implementation of the image class rather than being on display at the top level. So I can understand the top level in terms of the sort of higher level language of image and cropping without having to understand it, without having to kind of parse it in terms of a lower level construct like a NumPy array. The NumPy array is still there, but it's just now at the service of the higher level of that sort of intermediate language of images. So if I go back to my slides. So what we've kind of done is form like a little sort of layered collection of languages from the very highest level, which is featuring in the main part, the sort of the main section of the script, to this intermediate language of images and cropping and things like that, talking about, sort of pixel values, and then a sort of lower level in terms of NumPy arrays and image. And I didn't talk about it, but the image IO library, which is actually for loading in an image. I also didn't talk about the array equal that will come up in tests, which we'll look at shortly. So developing these layers of languages, as I say, it helps with our comprehension of the code and particularly navigating complex code bases, especially for those who are maybe not familiar with the code base. It reduces that mental mapping from implementation detail to concepts, which is closer to the domain we're trying to represent. These kind of layers, if you like, this is an example of encapsulation, or what's called in one book abstraction barriers. And the key thing there is that it decouples the implementation in this example of, say, the image class from how it's used. I can change the details of how the guts of the image class is implemented, but then code that uses that image class doesn't have to change. And that's really powerful, obviously. And I think one other way to look at it is that it helps to get the complexity of our software closer to the complexity of the domain we're trying to model. I suppose something we want to aim for. I mean, we may well be, trying to model something which is highly complex, but ideally we don't want to have to add much extra complexity overhead to the code that we're writing for that. So the next thing I just want to talk about is tests informing design. So probably everyone here has heard of like unit testing or something, or automated developer testing. And one of the key principles that you often read, particularly in people who are kind of to do with that sort of agile software development sort of movement, is writing code in a way that makes it easy to test, and particularly in an automated way. So one of the benefits that this gives is that the tests become like the first users of your code. And so if you're writing tests which are easy to write and easy to express, that usually means that the actual code you're testing is becoming more sort of decoupled and, in a way where you can use particular components or change particular components without having to change other bits, or be able to reuse components elsewhere. And one thing about tests is that they shouldn't be concerned so much with implementation details of what they're testing, but they should be testing the requirements of the behavior on those objects. And then finally, linking back to kind of like the first principle, so we want to try and make the tests as easy to read and as simple to express as possible, partly because, to check that a test is correctly implemented, we're usually just doing that by eye, but also because as we're kind of, if we're trying to build up a sort of language to express a problem, being able to succinctly express what the requirements of the problem are in a kind of declarative way is an excellent way of actually sort of capturing what concepts are important for us to move over into the main code base. So if I again switch over to my code, so the first version of the code that I showed didn't actually have any tests, because it was really just a sort of read inputs, and there were no intermediate functions to provide any testing there. Oh, sorry, just arrange my windows. Over on the right here, I've got my unit test file for this updated version. And again, not going to go through all the details here, but if I just scroll down to so this class here is concerned with testing the main kind of workhorse function quarter image here. There's only 2 tests here. In reality, you probably want more. But I suppose the main thing I want to point out here is I've tried to keep these tests short, no more than a few lines. but also expressing them in terms of the sort of higher level language constructs that I've started to create in terms of images. And ideally, a representation, or sorry, the test should actually read like a specification of what I want the main thing to do. So hopefully here, if I have this test quadrant dimensions, half image dimensions, now that probably gives a clue already to what it's doing. But, I read this and I go, okay, I've got an image. I create an image in terms of some pixels. I then quarter up, so cut up that image into quarters. And then for each quadrant in those quadrants that I've created, I want to make sure that the quadrant's height is equal to the original image's height divided by 2, and same with the width. Okay. And then moving on, the second one, let's see. So in this second test, I've actually created an image now from some grayscale values. So I'm not going to go into detail of that. But the main thing to think here is this is an image. And if you think about it in sort of XY coordinates, roughly speaking, the grayscale value in the sort of the top left hand sort of block is kind of a 2x2 matrix of ones. Then we've got a 2x2 matrix of threes if we go to the northeast quadrant, and then the southwest quadrant, 2x2 matrix of twos, and then finally fours in the southeast quadrant there. So I've built up an image with this kind of block structure, and then I'm basically asserting that each of those quadrants has the 2x2 sort of block structure that I started with. But I'm trying to express the tests in terms of this sort of this high level language that I was creating. If I very quickly look at an earlier version of these tests, this is actually a similar version, but I'm using the language. I'm still using the language of NumPy arrays here. So I've got concatenating some arrays, and I've got checking that arrays are equal. Again, this is fine in a small thing, but ideally I don't want to be using a sort of lower level construct and having to mentally map onto, the actual requirement I care about, namely cropping images. So I think this is a way that tests really help to sort of develop that language that, develop the different levels of language that we ideally would like in our sort of software. And of course, tests come, with other benefits as well. They clearly provide a safety net against introducing bugs, so allow us to kind of change code with confidence that we're not breaking something, or at least give us more confidence of that. I already talked about how that often leads to smaller components just to make it easier to test, and that can encourage reuse of components elsewhere and decoupling in the code base. And again, this sort of clarifying this thinking in terms of how we express a problem and solve it in terms of these sort of domain languages. So the final thing I just want to touch on briefly is a notion of reducing dependency on unstable things in code. So some parts of code are going to be more stable than others. Some parts are expressing real sort of core logic, if you like, of the problem, which we would hope is not going to change too much. But there are other parts which maybe are going to change either in the future, or we just don't have much certainty about at the moment. And so one of the principles, this is particularly in the book Clean Architecture by Robert Martin, is to try and minimize the dependencies on the unstable parts, because if those unstable parts change, anything that depends on it, could well also need to change. And if you've got lots of dependencies going into that unstable thing, that can ripple out to lots of areas of the code base. And there's a particular technique which we can use called dependency inversion to help try and guard help try and build up these kind of little barriers, if you like, so that the unstable parts can change in a bit more of a controlled way without affecting the rest of the code base. And that's what I mean by depending on abstractions or interfaces instead. So just as a sort of thought experiment, if we're tasked with writing some code and to run simulations, and the person we're working with says we want to be able to run a new simulation model remotely from our laptops and store the results. Well, that raises a whole load of obviously a lot of that is ambiguous, like how do the results need to be saved for one thing? Is someone just reading them from console output? Are they saving it to a file, or maybe do they need to go to some sort of remote database? I mean, that's one thing, but okay, well, how do you want to give the input values for the simulations? Similar ideas, maybe from a command line or read from a file, maybe even through a web application. It's not uncommon, I think, particularly in a research setting, where you might have something where, oh well, we want to start using it just by entering values from a CSV file, but in the future we want to share this with others, and it might be nice if they can then enter the values through a web application. So the way that we're getting the data in is potentially going to change in the future. And of course there might be other things like how you run the simulation model on a remote machine, directly via a job manager, etc. I'm not going to go into a particular code example here, just in the interest of time, but let's suppose part of the code involves creating a job to send to the remote simulator, and as part of doing that, it will record the values that it gets back from the simulator. Okay, so initially we might just use some sort of class that writes to a CSV file. Now, if that is going to be used in lots of places, there's this CSV log, there's the potential that if we need to change that, we're going to have to then change calling code in lots of different places. And a technique we can use here is which is probably something that people have done either knowingly or unknowingly, is to introduce something like an abstract base class, or called like an interface in Java or C#. There'll be other people who know better. I think C++ also has the notion of an abstract class. But basically this idea of specifying the API, the sort of method interface to a class, and depending on that instead. And then the idea is that the CSV log is something which would then implement this abstract base class. And if we're just depending on, in this case, an abstract base class, it doesn't matter what's ultimately implementing that, as long as it adheres to the interface. So that gives us the power to actually then substitute in different implementations. So maybe in the future, if we need to be able to write the details to my MySQL database, then we could implement that. Or for the purposes of testing, we could even just have a sort of in-memory log, which maybe just caches the values, in a list structure or something like that. So that sort of flexibility can both help add on extra functionality in the future and also help with testing. So, and that's kind of that first point is what I've just said, as well as the second point. Another aspect here is that we can, even if there's kind of uncertainty about how that, in this case, that sort of simulations log is going to be implemented, we can still develop code that uses that if we're agreed on the interface that it exposes. And so that means we can sort of defer certain decisions or wait until later to implement certain things. So that's what I mean by a kind of asynchronous development of code. We don't need to wait for things we develop to have been finished before we can continue on with other parts of the code. And another aspect, which I think can be sort of potentially overlooked, is the need to shield against third-party changes. We can sort of wrap third-party packages in sort of appropriate abstractions, and then if they change, we minimize in the code base where we need to change those, where we need to make those changes for our code still to work. So I guess in the last sort of just minute or two, I just want to say a little bit about the difference between, or looking at the difference between a kind of evolutionary approach to code and upfront design. So coming back to this, as I said, the sort of ideas of embracing change or being able to respond to change have sort of bled into how we design software. And in particular, we could sort of describe this as a sort of evolutionary or emergent style of design. And this would take the kind of view on the top that software design is kind of a combination of code development practices that allow us to respond to change, combined with very much a sort of greedy kind of approach to feature development. We just focus on one feature in the here and now. We get that working, and we trust that our design will, over time, kind of evolve and shape itself around more and more of the code base as more and more of the sort of problem domain as more and more features are added. But there's always a bit of a counterpoint to this, and this is talked about in John Oosterhout's book, A Philosophy of Software Design. He terms it in terms of avoiding tactical programming and being strategic. And the basic idea, I think, here is, well, with this evolutionary design, how do you know that you don't sort of go down one path and tailor your design to something that in the moment seems very applicable, but later on down the line is going to actually need quite a lot of rework and maybe undoing and refashioning. So, of course, whenever there's this sort of contrast, you can talk about a spectrum, right? And at one end of the spectrum, we try to plan every little detail up front, not leaving any source of ambiguity. And at the other end of the spectrum, we just, keep our blank page, put it to one side, and just start, looking at the code and implementing features. And each of these, almost certainly is just is an extreme to be avoided, but it's worth thinking about where on that spectrum do we want to be. And I think one thing I sort of feel is that I would be more inclined to lead more towards that second half, that sort of design as you go side of things, or at least not feel I have to plan too much up front before I can get going. Because if there are techniques that allow us to sort of evolve software, that just gives us more, license to be able to do that. And just to end with a couple of sort of analogies here. So I tend to like to think of design as first maybe putting in a sort of basic structure, a bit of trellising, which gives the general idea of where I want the software to grow. But then I sort of, will not spend a huge amount of time on that, and then use these techniques to sort of allow the actual sort of plant to kind of grow in the way, but, held in a bit of structure to just encourage the general direction. Or another one maybe is sort of climbing, how do you get to the tallest peak in a mountain range? Well, there's always the risk that if you just start at something that looks quite tall, you might get to the top of that and then only look at, only get to the top and realize there was that bigger peak ahead. And so maybe another way to look at it as well, design is kind of like surveying the whole range to get a general sense of where I think the sort of the tallest peak is, put myself somewhere around there, and then let this more sort of evolutionary approach take steps more to ultimately get to the summit. But I don't need to have figured out how to have got to the summit exactly before, I set out. So there are some perspectives. I'm sure there'll be stuff that can be, well, maybe there'll be stuff that can be disagreed with, or certainly stuff or situations where it's not so applicable. But I hope this has at least sort of provoked some thoughts and reflection, or will do over the coming days. And that's all I can really ask. And I look forward to the discussion now. So thanks so much for listening. Here's a list of, so the top sort of references kind of features more heavily in the preparation of this talk, but below there's also, stuff that I've also sort of dipped into and read, and, might be of interest to people. So yeah, thank you very much for your attention.
Thank you, Tom. Thanks for the presentation. Sorry, I'm being white balanced. Yeah, so we've got more or less 15 minutes. So we've got some time for some questions. And so first, maybe if we go for some directed questions, and then depending on how we get with that, we can open it up to kind of a bit more of an open discussion. But yeah, if anyone wants to use the raise hand feature in Microsoft Teams, and then that'll tell us an ordering of questions. Yeah, got a question from Linus.
Hi, Tom.
Hello.
Yeah, thank you for the presentation. I wanted to say for that like upfront versus evolutionary design, for me, definitely I've seen myself go from the upfront end much more towards the evolutionary. I was wondering if you had like a similar journey or the other way around, if there were specific things that kind of made you change your mind, and if you think that's like a general trend in software design. Like, do you see that in other people? Do you see anyone who does the opposite?
So I think you'll struggle to find someone who is very much on the completely design everything upfront approach, possibly, except for very small. I'm kind of hypothesizing here because I really don't have a huge amount of experience, but maybe smaller systems where there's a real need for like proof of correctness or something like that. That might be something where much more upfront work is done. But I think certainly the way that software development and thinking around that, particularly in industry, has gone over the last 30 years, I would have thought there is more of a move towards a kind of more evolutionary approach. I interestingly maybe sort of started on the, because I think naively you sort of think you need to sort of, it's good to design everything up front to avoid nasty things coming up later. But then just through experience of being on projects where there's a lot of ambiguity or, uncovering new requirements as you put something in front of people, I inevitably have moved more towards being a bit more comfortable with ambiguity and trying something, putting it in front of people, and then seeing how it needs, and then seeing what can change in kind of response to feedback. I'd say maybe like a year ago, I had definitely drunk like the Kool-Aid of, really kind of almost focusing mostly on the code and not really doing much of, upfront design at all, if any. And I've sort of moved more away from that because of this, I think, of this problem of sort of getting stuck in sort of local optima, if you like, of thinking that you've gone down a right path and then needing to undo stuff because there were bigger picture things which you could have foreseen. So I've definitely moved away from the right-hand side of that spectrum over the last sort of year or two. But yeah, I'm sure that the idea of sort of complete upfront design is almost dead, basically, now. But it maybe there's also an aspect of personality in terms of how much ambiguity you're happy to tolerate or how much you feel you need before you can make a start. At the same time, I also feel like to some extent I need to be able to map out a whole most sort of a problem before I can start writing some code, but then I'm happy to adapt that as the kind of code teaches me and how it as it feels at the time. So yeah, it's a bit of a sort of nuanced thing, and I maybe sort of veer from side to side every now and again on that spectrum in a way.
Thanks, Tom. Thanks, Linus. That was a good question. Yeah, it's kind of like you want to design, you want to make the whole piece of software once and then use that as your design to make it a second time. Anyway, we have a question from Anders.
Yeah, so this is a question regarding testing. Thanks so much for the presentation, Tom. I may read it wrong, but you said that by testing, it can encourage, or it will encourage, more likely better decoupling of the code or compartmentalization. Isn't how, because if you, that doesn't that depend? It's like chicken and egg. So if you test, depending on how you do the test, you might stimulate that. Or are you saying that, do you see what I mean?
So I think I might see what you mean. Can I maybe, if I express it this way, it's all very well saying, okay, you write the tests and then, the code design will sort of help to come out from that. But how do you know what tests to write to begin with and how to express those tests? Is that kind of part of what you're thinking there?
Yes, I guess so. I mean, it's, obviously test-driven development is a nice thing, but in reality, it's not necessarily practiced a great deal for various different reasons. That maybe, but even if you did test-driven development, if you are, as you're saying, you're using the primitives, so NumPy in this case from the very beginning, what difference is that going to encourage? So I guess it's some recommendation as to how you could really stimulate that actually doing the test-driven development, and when you do testing, such that it's more likely that you are going to get more compartmentalized than decoupled code.
Yeah, so I think there's two things there. So the first thing is, so you talk about, well, if you implement your tests in terms of, like, in this case, NumPy arrays, aren't you kind of leading yourself down to potential problems there in terms of and maybe not creating these sort of high level languages that would be helped. I think I agree, I agree with that. And so I think part of what can help firstly is, and this is maybe where there's a bit of sort of pen and paper upfront design goes on, trying to model the problem, not in terms of code, but just in terms of concepts, and sort of put names to things. So I start with, I start with this problem of I want a script which can take an image and cut it up into 4 parts. Okay, so how do I express that? Well, it needs to okay, so I've got an image. Okay, that's an initial concept. I'm then cutting up that image. Okay, well, that's a perfectly good term. Although, I've also seen other people, or, I know this notion of cropping an image. And okay, well, if I have cropping, I can then break up the image into parts. Maybe further on down the line, I might want to combine images, and so maybe sort of paste images together. So, and here I've not talked about anything about how I represent those images in code. I'm just talking about how can I express a problem and there's a whole kind of approach to doing this called domain-driven design that kind of makes this more formal, and they'd use the term ubiquitous language here. So, and I think once you've got that image, it's then perhaps being sort of willing to say, okay, well, I'm now going to create a class or a function or whatever it is to directly represent that. And let me just think about how I want this class to actually act in terms of those fundamental, that sort of fundamental language I'm starting to build up to express the domain. So, I guess going back to this, it's trying to express the requirements directly in terms of sort of code constructs that I've created, so implementing the language myself in the code. So I think that's one aspect to it. But the other aspect as well is, as we test code and we think, oh, I better make sure it does this, and that it works correctly in this case. Often I think if you end up starting to find a situation where you're having to write several lines of setup code, and it's starting to obscure kind of how crisply the test expresses the thing that you're ultimately, the requirement you're ultimately trying to test, the part of this, what you're trying to say about the system overall. I think if there's a lot of kind of preparatory setup, or that you're needing to do, or you need to understand a certain mental mapping to interpret the results of the test, I think that can become a bit of a sort of red flag that maybe you're using a sort of level which is a bit too sort of primitive, and that maybe there are other concepts waiting to come out that would simplify the expression of the test. And the other point I had was and so actually trying to write a sort of thorough test suite, often we then need to kind of break things down into smaller parts, or supply ways to actually make it more easy to supply input data to, say, to create a class, or input data to a function to actually be able to test our code. So, but it's all kind of broadly around making things easy to test, and that kind of lending itself to decoupling. So if something feels awkward or difficult to test, that's probably a suggestion that there's a bit more work that could be done to try and decouple things there. I don't know if I don't know how well I've answered your question, but that's my attempt.
Very thoroughly. I think that's a very good answer. Thank you, Tom.
Okay.
As a somewhat related but kind of aside, in terms of this this test function that we have on screen. So if you go back
that we did have on screen, yes.
Yeah. I guess there might be some argument that these aren't necessarily unit tests because they do rely on these lower level constructs. I don't know how. Maybe that's kind of an extreme view, and maybe to actually get around that, it would rely on way too much. For what's a relatively simple problem, but kind of actually bringing in these other concepts, and I don't know, maybe mocking some of the results that are actually called inside the function to kind of get around that sort of logic.
Right. So are you talking about things like, well, this test for image cropping into quarters is using the from grayscale class method of image, it's using, quarter image is the thing we ultimately want to test, but it's got this other thing, and we're also talking about still talking about NumPy arrays.
And the NumPy arrays, yeah.
Yes. So right. So two things there. I personally don't find being strict about a definition of unit test particularly helpful, and I think even that it becomes very kind of it feels like it's a vague term already, and I think what's more important is expressing requirements for the overall system, and using succinct code to kind of express that. And so if that means using more than one method, for example, personally, I'm absolutely fine with that. There's probably others who that would disagree with that, but that's at least where I am currently on the journey. As for the thing about we're still using NumPy arrays, yeah, so this is something I did think about preparing this talk, and I think if I had more time, I would have asked the kind of rhetorical question, are we done here? And the thing that kind of well, there's one thing, we have to sort of there's going to be some way we get values into this class method. Now, in here, it might be in terms of a NumPy array. It could be a list of lists. If we're fundamentally talking about a sort of square array of numbers, which is ultimately what it needs to take in, there are several ways that could be represented. They're still using lower level constructs. I personally don't think that's a problem, because often you need to provide something lower level to actually create the higher level thing. So I think that's okay. Where I think there's perhaps more of an argument to make, and it's maybe not so much here actually, but at the top here, I keep using this term pixel, okay? grayscale pixels, the pixels as an argument as an input to the initializer for image. I've got any others up here. I've even as part of the unit test for my image class, where I'm just testing basically the initialization and the values of some attributes. Again, talking about pixels here, and I've still got a numpy array equal thing going on here. And as I was writing this, I was finding I keep having to write this annoying third dimension. When I'm thinking of an image, I really am only and cropping it. I'm only caring about 2 dimensions. I don't really mind what the RGB values are. So the fact that I'm having to do this extra work, or there's this extra thing I'm having to sort of put in, just to kind of obey the obey the gods of how it is at the moment, that maybe suggests there's another abstraction that could come out of this. Maybe that's the concept of a pixel and a square array of pixels as kind of being, a key part of an image. So that's maybe one area I would argue, actually, maybe we're not done yet. And here's something to leave people to think about, and it's something that bugs me in this. There's this notion of Yagni, which I know you'll know, Stephen, but this concept of you ain't going to need it. And I think there's often a tension here between introducing more kind of code constructs to express things more cleanly, but maybe in a way which is ultimately not going to be used in production. And you could ask, well, do you actually need that extra construct? I don't have an especially good answer to that, except to maybe say, well, I think maybe I'd consider Yagni in terms of the kind of end features that a user gets, and then I'm going to sort of try and write in a lean way, but I'm still going to make my code expressive, and introduce constructs that help me write expressive unit tests or expressive developer tests, for example. As a side note, the from grayscale class method here is not used anywhere in the main code base. It was purely introduced just to make it a bit easier for me to actually create some images for testing. So that's maybe an example where I've added something which might not strictly be needed, but it's helped me develop the language and develop my, and develop the expressiveness of the tests.
All right, yeah, thank you very much, John. Okay, I think we're out of time in terms of our allotted slot. So this just leaves me to thank Tom once again. And yeah, thank you all for joining, and look forward to seeing you again.
Cool. Thank you, everyone.
Thank you.